So far, if you've been keeping up with the class assignments, we've talked about how to make a path analysis, but we really didn't get into fit indices yet. We mostly just were looking at like how does the code work, how does lavaan work, and so this assignment will really get you into building and editing models along with fit indices and model comparison. So we're going to add a little more on today. Alright, so what I've got is this example, I think from the Klein structural equation modeling book, that is sort of two types of environmental components, mother aggression and mother withdrawal, with two sort of genetic components, or that's how I'm going to describe them, age and education, if we use education as a proxy for IQ. Child conduct problems, so more problems, and child emotional. So think about this as sort of attachment. Okay? And so what we're going to do is we're going to create this model and then do some model editing and look at fit indices. Now, one thing we didn't do when we tested this model in class is we didn't correlate the error terms because we weren't quite there yet. So I'm going to leave those two correlated errors out for the moment, although obviously they do have the potential to be very correlated, but for this example I'm going to leave them out. Right? So the data given in the book is a correlation table. So this is the lower half of the table, so we'll use that code. So what we're going to do is enter the data first. So this is going to be data.core to make this a correlation table. And so that's going to be the lav matrix lower to full. Okay, so remember that this code allows you to type in only the lower half of the matrix, and it will fill in the rest. So I'm going to enter all the numbers I have here. So this makes it easy when it's actually only the lower half given to you. And remember that if you get a p, 0 error, that means that you left off a number, which I did in one of the last videos. And negative 0.05, negative 0.03, negative, whoops. So the negatives do matter, make sure they're in there. But remember that R doesn't care if you enter zeros before the decimal or the 1.00. So negative 6, 0.41, and 1. Okay. So that code should give me the entire data set. So I'm going to use RStudio here. There we go. Yeah, close that file. Give me a new one. Okay, so always remember, start with the libraries. Okay, let me clear out all this other stuff I had open before. So we got a nice clean window. There we go. We got semPlot and lavaan to be able to do the structural equation modeling and to draw the pictures. And then I've cut and pasted my correlation table. Okay, remember, oh goodness, that took a minute, that the correlation table that you get will not, have the labels on it. So the next thing we're going to have to do is give it labels. So I got row names for my data set is, equal to the column names of the data set, so we can't name them accidentally the wrong thing, although you can misspell them. Equals, let's combine those, so concatenate function, and let's look at what my options are here. I have it in order, so aggression, withdrawal, education, age, emotion, and conduct. So I've got aggression, withdrawal, I've already forgotten. Small working memory. Education, age, emotion, and conduct. Education, age, emotion, and conduct. Okay. So that should give us the row and column names for our data set. Perfect. Now we want to create the model. So let's look at the picture here. And I'll create it up here so we can see everything at once. There we go. And so I'm just going to type the code for the model, and then we'll add the wrapper around it so that R can understand what's going on. And so I'm going to start here. So I got child conduct is approximately, and I'm going to all the paths going in. So aggression plus age plus education, right? So aggression, age, and education. Emotion is approximately age plus education plus withdrawal. And then let's work our way this way. So I got education is approximately withdrawal. And then age here is approximately aggression. And aggression and withdrawal are correlated. Now, because they're both exogenous variables, they will get correlated automatically by lavaan. And if you try to include that code to help to correlate, it gets kind of grumpy at you because it's going to do it for you automatically. But I do want to include these double paths here. Now, this is the way the model is drawn, but honestly, that is a covariance error, indicator. I'm sure there is a reason, and it's listed in his book, for why there is a path from education to age and age to education. But for me, when I'm thinking about this sort of path, that's going to be 2 degrees of freedom, and I'm essentially saying that I don't know what order they go in. And so I'm going to covary those, and mostly so I can show you what the covariance code is. You can do them as age is approximately education, and education is approximately age. But that seems like I'm losing an extra degree of freedom for what amounts to a correlation between the two. And so the way to do correlations, or covariance arrows, is double tildes. So age and education are covaried in this model. Okay. Now, I don't need to covary aggression and withdrawal. It will do it for me. So I'm going to copy all of that, go back to Studio. Okay, so we got to include our code so that lavaan will know what it is. So model is, and then open quotes. I'm going to use all this code here. Okay, I'm going to run that. But that doesn't actually do the model for us. It just sets it up. So let's run the model. Let's save this as epath2.r. Alright, there we go. And so what I want to do now is save the model. So I'm going to do model.fit equals, and we're going to do sim because this is a path model. I'm going to run the model, and then we're going to include our sample covariances. So sample covariances equals data.core and sample number of observations. So sample inobs is, let's see, n is 200. Okay. So let's do that. 200. Okay. So I'm going to run that. And of course I didn't spell something right, so let's see here. We got conduct is approximate age. Let's see, it sounds down here. Age. Oh, I called emo. My bad. Emotion. There we go. So now this time it should match. Yay. Alright. So what we've been doing before is a summary of the model dot fit, and we've asked it for standardized equals true, and then that's where we've stopped. So let's look at that summary. Right, and so this is a correlation table that we've entered, so it's technically already standardized. And so I can look and see that a lot of these are non-significant, right? So conduct, aggression doesn't predict conduct. Wait, where's my P? There we go. Education doesn't predict conduct. Let's see. Education and withdrawal don't predict emotion, but the rest of them are significant. And then we have our variances down here. Now, what we want to add, so let's go back to the assignment. So program the model, run the fit of the model. We did that, but we haven't really looked at the fit indices. There's two ways to do this, and I'm going to show you both. Okay. So one way to get fit indices is to do fit.measures equals true. I think that's what it is. Let's try it. So we run fit.measures equals true as part of the summary, not part of the actual structural model. So this is the summary part. And it will pull up a whole bunch of fit statistics here in a nice pretty layout. So let's copy that and I'll walk you through what they are. And then we'll talk about the other way to get the numbers you need. So I'm going to paste those down here. All right, so one at a time. What is everything? So number of observations is n. That's great. The estimator is maximum likelihood. That's the default. That's what you probably want to use. Now the minimum function test statistic is appropriately labeled, but it would be better if they actually called it chi-square. So this value right here, 10.38, is chi-square. So I don't want to write that here, 10.38. The degrees of freedom for chi-square is 4. And my p-value is 0.04. Okay, so it's almost not significant. Now, remember, it's a catch-22. The larger the sample size, the more likely chi-square is going to be significant. Larger models tend to be significant, and you don't want to be significant. And so chi-square isn't the only fit indice we're going to use because of the problems with it. Right, so that's all of that. Let's look at what you get next. The model baseline model is the null model where basically nothing is related to each other. So you want that to be worse than your programmed model, and it is. Chi-square is much larger, so these would be if every path is 0, and you want that to be bad. That indicates that at least your paths are somewhat good. So I'm not going to include that anywhere. The comparative fit index is a popular fit indice because you can use it to compare models, and the Tucker-Lewis index is also pretty popular. Now, CFI will always be higher than TLI because of the way the math works. And they're both scaled in a larger direction. So closer to 1 is better. So 0.9 and up tends to be considered pretty good. 0.95 is considered excellent. Anything less than 0.9 tends to be considered kind of bad. So we got one good fit and one bad fit. I'm going to ignore the log likelihood ones and look at this little group right here. I happen to like AIC, the Akaki Index, and I'm sorry if I'm butchering that poor man's name. And that is a fit indice that you can use to compare models. And so I could look at model 1 and this model 2 we're going to program here in a minute and look and see which one's smaller, and the smaller one is usually considered better. Because these include penalties for more model complexity. And so it tends to favor a model that's simpler. And sort of the Occam's razor idea, the simplest solution is often the right solution. And there are a couple of times we'll talk about when you won't necessarily want the simpler model, you'll want a better fitting model or a more theoretical model. But in this case where I'm sort of giving you a story on top of a model that I'm not even sure I'm explaining it totally right, just to use as an example, we'll see which one has the lower AIC. Okay, you can also use the Bayesian information criterion or the SABIC, the sample size adjusted Bayesian information criterion. I just feel like the AIC is a more well-known and used one, but the Bayes ones are popular as well. Okay. All right, so REMC is kind of required for publications usually. It's a pretty popular fit index, okay, and it is scaled on the low end. So a good REMC is close to 0, is 0. And if you think about it, the REMC and the SRMR, the one we'll do here in a second, are the residual statistics. So they're essentially how different is the covariance table or correlation table that you reproduced from your model to the one that you entered. And so you want the difference between those to be really small. The comparative fit indices, the CFI, the TLI, and the NFI, are ones that you want to be really large because they're essentially effect size. And so they're sort of 1 minus the residuals. That's an oversimplification of their formulas, but that's the basic idea. And so you want them to be large. Now the AIC doesn't really have a scale in the same way, so that's why it's used more for model comparison rather than, it doesn't have the kind of cutoff criteria that people have adopted. The 95% confidence interval will tell you like how well your model would hold up if you know, in the sense of a confidence interval, if you run it so many times. And you want the confidence interval to also be within the range that we would consider excellent, and it's not. So for RMC and SRMR, a model that's less than 0.06 is considered excellent, 0.08 is considered good, 0.10 and less is considered moderate, and if you're getting over 0.10, people will just kind of scoff at your results. And those criteria, I think, are in the Hugh and Bentler paper. They tend to be cited a lot as the cutoff scores for those, although remember, cutoff scores have their problems too. So our RMC is in the sort of acceptable, it's at least okay region, but the 95% or the 90% confidence interval is not so good. Okay. I have always seen the next line down, p-value that RMC is less than 0.05 as p-close. So p and then close. I think you could just call it p and get away with it, but what that essentially does, is it tells me the likelihood that p-value is less, that RMC is less than 0.05. And so you actually want that to be a big number. So I've seen cutoff criterions as like 0.5. So you want the probability that this number is less than 0.05 to be very high. So you don't want to reject the null. So this is really backwards to the way that we traditionally think about hypothesis testing, where we want the likelihood of it being 0.05 to be really high because we want that null hypothesis to be true. And so that would be the null hypothesis anyway. Okay. The standardized root mean square residual, okay, or SRMR. Sometimes you'll see it as RMSR, just depends on the day. It's 0.05, so that one's actually a good statistic. So we've got a weird mix here of okay and bad statistics. Now the other ones I have listed here are ones that I have traditionally used, like the normed fit index and the ECVI's expected cross-validation index for model comparisons, but they're not part of the fit.measures piece. So can you get them? Well, yes. Okay, so remember the question with R is not can you do something, it's how. Okay, there's a separate command, it's fit measures, okay, very similar, no dot. And you do the saved lavaan code, so model fit. Oops. Ooh, don't do that. That won't run. Dear possessed computer. There we go. And this is the less pretty version, but you get a lot more information. So you'll get the number of parameters, the degrees of freedom, and so it's all explained in Appendix A of the Buchanan book of what everything is in here. But I can get the NFI here, so 0.92, so the normed fit index. Yeah, so that one is in the good range, or acceptable range anyway. And then I can also find a bunch of other stuff. My ECVI here is last, so 0.192. Now that one doesn't have a cutoff score because it's more for model comparison. So just to give you something to look at. All right. So we've got fit statistics. When I say this is a good model, I'd say it's a mixed bag. About most of the fit indices are good, but not all of them. So let's see what we might be able to do better. But first, let's create that model picture using semPlot. So we're going to do semPaths. It's the code for semPlot. I'm going to include my saved lavaan code. So model fit. We're going to do what labels to get the parameters. and then layout, oops, wrong one, and let's try tree, why not? Alright, so that created me a picture of that model. Not quite as pretty as our drawn one. Let's try spring, see what happens. That's a little better. And what we're going to do is take out 2 of the paths, okay, or 2 of the squares actually. So quick warning here, look, see this dotted line? That is the covariance that it automatically did for you. And so I said I didn't need to include that code because it automatically did aggression and withdrawal. So if I go back to Word here and look here, it did that for me. So I didn't have to add that to my model specification. Okay. The other thing you can see is the covariance between age and EDU has got double-headed arrows. So it doesn't really draw them curved except for the error codes out here. So you just have to look for how many heads there are on it. Okay, let's try a second model where we take out something. So I said we could take out either the environmental component or the genetic component. Okay, so let me start, I'll work both of them by taking out aggression here. And so how would I edit my code? So let me copy this here and just take out aggression and withdrawal. So we've got aggression here and withdrawal here. So that would mean these 2 things also need to go. Okay, so I've got age and EDU are still going to be correlated. But now think about it, I don't have these 2 paths out here, so there's actually nothing predicting these 2, so I don't need this line. But we'll run it just to show you what happens when you specify something you don't really need to. Alright, so let's do model 2 here. And then I'm going to cut and paste this to save time because that's a little faster since it's the same data set. So from here, what I need to do is change at least the model I'm running. So I'm going to call this model 2, the model fit 2. So I'm going to kind of change these throughout so that I have it stored separately. So I'm not overwriting the code I've already done. So let's run this. Okay, so here's the grumpy error message that I apparently did not change my emotion. First problem. Let's try that again. Right? And then now it says the model syntax includes variance, covariance, intercept formulas involving exogenous variables. So I tried to add in that age and EDU correlation because that's the way I know I'm supposed to draw it. And then it's like, hey, don't do that. Leave them alone. Or use fixed x equals false. So if you wanted to turn them off, you could actually do fixed x equals false. Or I can just go, oh yeah, sorry, you're going to do that for me anyway. Let's just take it out. Okay, so now it runs fine. So I'm going to take my summary. And so I'm looking at this model, the quick summary of the paths. I still have some problems with education predicting conduct and education predicting emotion. So it looks to me like age is doing all the work in this model and education not so much. And so what I would have to do is figure out if that was the best model. So let me look here at my fit indices, and you'll notice something odd, that you have 0 degrees of freedom. Let's see if we can figure out why. Let's have it draw the picture for us. Okay. And so it automatically added age and education, a correlation between them, but you'll notice that that should have only left me with 1 degree of freedom if we had counted it out, that it also added this correlated path between conduct and emotion. So think about the model that you have right now. You have conduct equals age plus education, and emotion equals age plus education. So that's basically 2 unrelated regressions. Okay, so it's actually 2 just essentially correlated regressions. And so because they're not connected on on an end here. Essentially, it added that correlation for you. So covariance. And so you kind of ran out of paths. So your fit statistics for this are essentially going to be perfect because your degrees of freedom are 0. Okay. I'm sorry, your degrees of freedom is 5, but your fit statistics are going to be perfect, not because they're 0. They will be if they're 0, but because you've sort of over-specified the model. And so everything fits perfectly because it's sort of, you've correlated everything you possibly could and connected everything you could. So this is generally called over-specification, where you've added enough paths that everything fits perfectly. And so I don't know that I want to waste my time with these fit indices because they're pretty much useless. They're all perfect. What I could do is compare the AIC and ECVI, so 2193 here. But the issue with that is that since the model is overfit, of course it's going to be better. Okay. And so I don't know that it was a good idea to really take aggression and withdrawal out. So let's try it instead by taking out education and age. So I'm going to take out education and age here. Oops. No. What did I do? I wanted to do that. Yeah. Okay. So if I do that, I have emotion is predicted by withdrawal, and conduct is predicted by, and let's see, emotion is predicted by withdrawal. Got it. And conduct is predicted by aggression. Okay. And I've taken out education and age. So I have a similar problem here with a smaller model. These are essentially two unrelated regressions. Before, at least, they were related in the sense that they have the same formula, but so it correlated these little regressions. But now these are fairly unrelated regressions because several of these variables don't connect at all. So let's see what happens when we do that. So this is going to be model 3. Okay, let me fix my emotion issue. Okay, there we go. I'm going to copy these lines again. And let's change everything to model 3. All right, so we're going to see a similar problem. Let's see what happens. Okay, so now I've run the summary. Again, we're having trouble predicting emotion with withdrawal, but everything else looks significant. And then this time, we've got some fit statistics. So we could use this model and see what happens, but let me create the picture. So you'll notice because they were sort of unrelated, it added my exogenous covariance, and it also added this covariance over here to make them connect to each other. And so that was an automatic thing. I did not program that in. So let's look at the fit statistics, a big list of them, and compare our two models, since we couldn't compare the other one. Oh, there we go. I want to find chi-square. So if I'm looking from this one, it's actually called chi-square, which is kind of nice. So I got 2 degrees of freedom is 2.208. And then my p-value is 0.33, so it's not significant. That's good. And then let's cut all that out and look at the CFI here. So go down to here, 0.995, that's good. TLI is 0.987, also good. I'm going to skip NNFI because that's the non-normed one, so when he's normed, 0.951. And then let's keep going until we get to REMC. Oops, I think I deleted AIC. There's AIC, so I'm going to use this AIC value. And it's pretty clear which one's going to be better, right? Just looking at the numbers. So the REMC is 0.023. The 95% confidence interval is lower 00. Oops, wrong place. 2.14, so still above the range that we would want. And then our p-value, so the probability that it's less than 0.05 is 0.495, so we're pretty close to that 0.5 criterion. And my ECVI, oh no, SRMR. SRMR is 0.037. So that's a good statistic, and my ECVI is 0.061. Okay, that being said, which model is better? Well, there's several ways to compare models. And so if your models are nested, meaning you can create one model from another, you can do a chi-square difference test. In theory, these models are nested because what I have done by taking out these two variables is set their paths to 0. I could continue to have this picture, but I could just force all of these paths to be 0. So I could do a chi-square difference test. So what you would do is do difference in df, okay, that's 2, difference in chi-square, and that is math, so 10.8, 38 minus 2.208 is 8172. Okay. And so now I need a table. So is that a significant difference? Well, I usually have a table. Okay. Sure, fine. What we will do is pull one up on the internet. Since my computer doesn't want to find my chi-square table that I know I have saved, we will go to my favorite chi-square table, which is this one. Okay. So what you want to do is go down to the number of degrees of freedom difference, so it's 2, and look at 0.05, and so it's 5.99. So that's the cutoff score, or the critical value for the difference test. And so my critical value is 5.99. And so is my difference score greater than my critical value? And that answer is yes. And so the models will be considered different, and the model with the lower chi-square sort of wins. So a model 2 would be better. Okay, the other possible ways you can do this is the difference in CFI. So that's really popular for multi-group models. And so you subtract the two CFIs from each other. 995, you take the absolute value. Okay, so I got 0.049. And anything greater than 0.01 is considered different, and the one with the higher CFI wins. This would be lower chi-square. That's another popular one. And then the last one are these model comparison statistics, which are designed for that purpose. And so you would just look at whichever one is lower. So that would be model 2, same thing here. And so all indicators point to model 2. I tend to avoid using chi-square for anything because model nesting can be very confusing to people. And so if you always go with a CFI or one of the model comparison statistics, you can't really do it wrong. Especially if you decide to compare non-nested models that do not have a difference in the degree of freedom. So if they're both degrees of freedom were 4, that would make a chi-square difference test a 0, and that's not a thing. So I always tell my students to go with CFI or AIC ECVI because you can't really go wrong with those statistics. Whereas you could use a nested chi-square test in the wrong place. But this, I wanted to talk about it because it is a thing. Even if it's not necessarily appropriate for this model, it is something that people do. So I wanted you to know how it works. So which model is better? I would say the simpler model is better. And I don't know that it's the best model theoretically because it's not my research area. And I don't know if it's a good idea to include models that don't seem to be correlated with each other. So I should probably add a path that predicts the relationship between these other than the covariance that it added for me manually. And so theoretically, the first model may be much better, but like just straight mathematically, the second model is better. Okay. So let's interpret the loadings of the better model. So we'll use model 2 here, or this is model 3. So let me rerun my summary. Now when you're interpreting loadings here, it is treated in the same way that regression is treated. So I'm going to look at the estimate, and it says aggression predicting conduct, remember they're backwards, is 0.154. So that means for every 1 unit increase in aggression, I am going to get a 0.154 increase in conduct. Okay, so as mom gets more aggressive, more conduct behaviors happen. Withdrawal is not significant, so I would leave that one alone. And then the covariance between emotion and conduct is significant. So as we have more emotion problems, we also have more conduct problems because it's positive. So interpret them like you would a regression coefficient as B if you're looking at the standardized solution, which over here would be standardized all for this type of model. Since we don't have any latent variables, you would interpret it as a beta value. So for every 1 standard deviation unit increase, this thing changes 1 standard deviation units. So that's why some people like the unstandardized solution, is because you can think about it in terms of the scale of the data, whereas the standardized solution is really great if you are doing like a CFA and you're used to interpreting the kind of loadings that you get in EFA, or if you're wanting to compare things that don't have the same scale or compare across models. So a standardized solution is also a really good thing to have because you can use it for a lot of other functions. Therefore, that would be all for this assignment. So interpreting, think about regression coefficients, and so significance, you look at P. With a small qualification that anything with large numbers of people is going to be significant. So you might want to think about the strength of the loading as well, think about effect size, that sort of thing. We talked about fit indices and how those work, and then changing models and manipulating them just to see how we could compare things.